Welcome back to CS103 Machines, Languages and Computation. In this lecture we're going to look at sets again, but we're now going to look at infinite sets. That is ones where we can't enumerate all of the elements of the set in a finite time because they go on forever. Infinite sets are going to be really useful to us because when we consider what computer programs we might want to write, then that turns out to be the functions that will map inputs to outputs, and those inputs and outputs are both chosen from infinite sets. So let's have a look at them. At the end of the last lecture, I asked you to ponder on the problem of what you would get if you use set builder notation on this expression here. The set S such that it's members of the form 2n plus 1 and n is chosen from the set 0, 1, 2 or 3. So what set does that actually give you? Well, what we do is we consider each element of this set going into the formula. So we first of all consider n is equal to 1, put that in the formula, that gives us 1. Then we consider n is equal to 1, put that into the formula, that gives us 3, and so on, and we end up with the set 1, 3, 5 and 7. In other words, the first 4 positive odd numbers. So now let's have a look at infinite sets. As I've said, sets can have an infinite number of elements. We can talk about sets such as the set of all the whole numbers. Well, that's got an infinite set of elements. And it's got a name, Z. It's called Z because it comes from a German word Zahlen, meaning to count. And the set of all the whole numbers is the integers. Now this includes all of the positive whole numbers, 1, 2, 3, 4, 5, also 0, and also the negative whole numbers, minus 1, minus 2, minus 3, and all the way to minus infinity. And we might write it down something like this. So Z, well, it doesn't really start at minus infinity because it's a limit, but then once it gets going, it then goes minus 4, minus 3, minus 2, minus 1, then it's 0, and then we get started on the positive ones, 1, 2, 3, 4, 5, 6, 7, 8, and so on and so on, going all the way up to plus infinity. So if you tell me an integer, I can tell you the next one, as it were. I can just add 1 to it, in other words. So you can say, well, I think the biggest integer is 1006. Well, I say, well, it's not. It's because there's an even bigger one, 1007, and one bigger than that, 1008. So they go on and on and on forever. And similarly, if you tell me that the smallest integer is minus 568, I'll say, well, okay, then there's a smaller integer which is minus 569, and so on and so on. So it goes off in both directions all the way towards infinity. Another important set, and I've already introduced you to this, is the set of the natural numbers, which we denote as n. Now there's two versions of this depending on where you want to start. A very natural place to start counting with natural numbers is 1. 1, 2, 3, 4, 5. But if you ask the question, for example, how many apples are there in this shopping bag? Well, the answer could be 0 as well. So there's two versions of the natural numbers, depending on what you want to do. There's n1, which starts with the value 1 and then goes on. And there's n0, which starts with the value 0 and then goes on. We'll use both versions, but from the point of view of computer science, this is probably the most interesting. As I said, if you've got n bits, then the smallest value that you can represent with n bits, if you're just using it as a binary integer, is 0. You set all the bits to 0, you get 0. So 0 is a very natural place to start for computer scientists. We often start numbering the elements of lists at 0 as well. Another infinite set, and one that you're probably familiar with, although you don't know it's called this, is the one that includes all the fractions, all the decimals, all the irrational numbers. In other words, it's all the integers, but also all the values between the integers as well. The irrational numbers are things like pi and the square root of 2. They're numbers which they're not integers, certainly not integers, and you can't express them as fractions. And you might know that if you try to write them down as a decimal, then they go on and on forever, but they never repeat. So if you write down an x-axis, so say we're going to plot the graph of y equals x squared. We plot an x-axis and we plot a y-axis. Both the x and the y values are chosen from this set, the real numbers. So we'd say x and y are both elements of the real numbers. So they can have any value you like. So it's a continuum. Whereas the integers are like, there's one here, and there's no values between them. So the real numbers are a big continuum of values going all the way from plus infinity to minus infinity. One of the things to note here is that different sets behave in different ways. As I said, with the integers, there is the idea of a natural successor. The successor of 0 is 1, the successor of 1 is 2, and also the one that comes before. The one that comes before 0 is minus 1. This is also a property of the natural numbers. There's a successor, but there's another interesting property of the natural numbers, which is that there is there's a smallest element, almost like a first element. I said not to think of sets as having an order, but there is a smallest element, and so you've got a smallest element and then a successor function, which means that the natural numbers, either version of it, is a very orderly set of infinite values. Whereas the real numbers are not like that at all. And it turns out that if you take the real numbers and try to map the real numbers onto the integers, say, you simply can't do it. There are too many of them in some sense. And therefore we say that the real numbers is a bigger infinite set, has a bigger cardinality or a larger cardinality than the integers. And we'll explore that later. We're going to, for the moment, let's set the real numbers to one side and not worry about them. And let's just think about the natural numbers and the integers. Sometimes in our proofs, we want to use infinite sets, but ones that we don't actually have. So for example, I want to do a proof involving the set of all the odd numbers. Well, unfortunately, this set here, minus 5, minus 3, minus 1, 1, 3, 5, that's not one of our infinite sets. The odd numbers are basically, it's all the integers, but with the even numbers taken out. So every value in the integers, so if we look at the integers here, every value in the integers which is even, in other words, it divides exactly by 2, if we remove all of those, then we're left with the odd numbers. Another way of saying it is that the odd numbers you can get by taking an integer, multiplying it by 2 and adding 1 to it. That's another way of doing it. Okay, so how are we going to build this set? We're going to have to do it ourselves because it's not one of our pre-made sets. Luckily, we can construct the set we need using the set builder notation, and it goes like this. So here, on the right-hand side of the set builder notation, instead of saying n is a member of 0, 1, 2, or 3, a finite set, we've got n is a member of z, which is an infinite set. So how is this going to play out? Well, what we do is we think of it being, you take this infinite set and you multiply every value in that infinite set by 2 and add 1 to it. So, well, let's start with 0. That's bang slap in the middle of the set Z. So 0 is going to map onto 1. 2 times 0 plus 1 is 1. Then let's take the next value up, which is 1. Well, 2 times 1 plus 1 is 3. Then the next value up is 5, 7, 9. So we're getting all of the positive odd numbers. What about if we go to the negative values in Z? So minus 1 is going to map onto the value minus 1, exactly as we want. And minus 2 is going to map onto the value minus 3. Minus 2 times 2 is minus 4, and then we add 1 to it, and that gets us to minus 3. Similarly, minus 3 maps onto minus 5. So you can line the two sets up, the integers and the values that you get if you take the integers, multiply them by 2 and add 1 to them, and that will give you exactly the odd numbers. So in other words, by transforming each element of Z by 2, we can transform Z into exactly the set we want, and that's what we'll be doing in our proofs if we want to talk about the set of all the odd numbers.